As you know, we have fast reactions and slow reactions. Some examples of fast reactions are explosions, fireworks, airbags inflating. I've had the unfortunate experience of having an airbag inflate. It's a very violent chemical reaction, very fast. It occurs on a millisecond scale. It has to in order to save your life, but that's a chemical reaction that releases a lot of nitrogen gas very quickly. So those are fast reactions. A lot of reactions are really slow. For instance, the rusting of iron, oxidation of a penny. Try to think of a few on your own. There are many of both, and all in between, from slow, medium to fast. So see if you can think of some on your own, forward them to me, and we can discuss it when we start class again. There's a lot of writing on this page. I'm sorry about that, but since this is a video, you can pause it and read it a little bit, do the textbook reading, and try to digest all of this. The basic theory that describes the speed of reactions is called collision theory. We also can call the movement of molecules and atoms in a reaction, we can call it the kinetic molecular theory. We will talk further about that when we discuss gases and how they behave, but they both theories pretty much have these five components. Number one, reactants must collide to form products. That seems pretty obvious. The reactant molecules have to bump into each other for their electrons to be transferred. Number two, atoms and molecules move faster as temperature rises. Higher temperature means higher energy. Higher energy means more kinetic energy, so things move quickly, more quickly. Collisions have to occur with enough energy to break reactant bonds. That's called activation energy, and we'll talk about that in this video in more detail. Number four, collisions must have the correct orientation to form products, and I want to talk a little bit about that in a second here. And number five, reaction rate depends on reactant concentrations. So if you want a reaction to go faster, you can simply increase the concentration of one or more of the reactants, and that will usually speed up the reaction. So let's talk a little bit about this orientation effect. What does that mean? Let me show you this overhead here. And as it says, is atoms or molecules must collide with the right orientation. So let's look at a simple reaction here. This reaction of nitric oxide plus ozone to give you nitrogen dioxide and oxygen gas. This is a reaction that might be occurring in the upper atmosphere where the ozone layer is, and NO might come from industry or emissions from industry or car emissions and rise up into the atmosphere and cause the degradation of the ozone layer. So these are reactions that can hurt the ozone layer. A product of the reaction is oxygen, which is good for us, but being so high in the atmosphere, it may or may not ever get to us at sea level. But nevertheless, how does a reaction like this occur? Well, you can think of it in a few ways. This would be called an unsuccessful collision here. So you put the gases in a vessel, flasks, you heat it up, and what happens is the molecules start moving at random. Remember, we live in 3 dimensions, so not all collisions are going to be successful. What I mean by successful is I mean that the atoms have to line up with each other in just the right way. So this collision here that you see would not be a successful collision, because if we're going to make NO2, that's a nitrogen in the middle of 2 oxygen atoms. This collision here would cause a molecule that looks like NOO with 2 oxygens attached, which is not what NO2 is. And also, the oxygen molecule would not form if this middle oxygen would leave and be attached to this oxygen. So this is not a successful collision. To have the reaction occur, you have to have the molecules bump into each other with this orientation. The nitrogen of the NO molecule would have to collide with one of the end oxygens of an ozone. Ozone's a V-shaped molecule. And what's going on here, what these dotted lines represent, are bonds forming and breaking. So this molecule approaches this one. As their electron clouds overlap, the NO bond forms, and at the same time, this oxygen-oxygen bond breaks, and that is a successful collision, which you would get NO2 plus an oxygen molecule. But this doesn't occur 100% of the time when NO and ozone bump into each other. It only occurs maybe 1% of the time. It's hard to really say. But in order to get enough products, you have to stir it for a long time. That's why we stir and mix reactants in real industry in reactions, because it just takes a while for enough molecules to collide correctly. And eventually that will happen. Some reactions take minutes, some take hours, some take many days or even years. That's what kinetics is. It's describing the rate, how fast or slow a reaction is occurring. So how do all these effects influence the rate? What I've summarized here is all these effects will speed up reactions. A solvent is a liquid, usually, that you use in a reaction to provide a medium for the reactants to combine. It's usually a chemical that won't chemically react with either of the reactants, but it just provides a place for the reaction to occur, and it dilutes the concentration down to a level that is just right for the reaction to occur correctly. But it increases the number of collisions, so it increases the rate. These effects are all going to cause the rate to speed up. So to decrease the rate, you can just try to think of some other ways that can happen, and we can discuss that during class. Increase in surface area. How would we do that? Well, let's say you had a solid compound you wanted to use as a reactant. Well, you would crush it up into a powder, and that would increase the surface area, and therefore when you use it in a reaction, that would increase the number of collisions as well, so the rate would go up. We generally heat chemical reactions, so we increase the temperature, and as I said, that increases energy of the molecules. They'll move faster, therefore they'll bump into each other more often, so the rate will go up. This is what's happening when we cook food. Molecules are moving faster, and the reactions that would naturally occur are greatly sped up. When we keep food in a refrigerator, we're just slowing down these reactions that would naturally happen. So when we cook food, we are speeding them up. Cooking food also creates new compounds that make the food taste better. We can also increase the rate by increasing the concentration, and again, that's pretty obvious, I hope. It just means that if you have more molecules per unit volume, they're going to bump into each other more often, so again, the rate would go up. And one of the most useful ways to increase the rate of a reaction is to use a catalyst. So in industry, in the car industry, coming out of your car's exhaust is what's called a catalytic converter, and it's usually made out of a metal compound, usually platinum or palladium, and the gases pass over that catalyst, and the noxious, poisonous gases that are coming out are converted into relatively harmless gases like carbon dioxide, water, NO2, things like that. A natural catalyst, a biological catalyst, are known as enzymes, and I want to talk about them for the rest of the video. So to summarize an energy diagram that has a catalyst in it, I've drawn this picture here. How does a catalyst work? Well, this black reaction profile represents a reaction in which there's no catalyst. So a catalyst provides a different pathway. This blue pathway you see here is the pathway that a catalyst would provide the reactants. The energy of the reactants is here, going on to a lower energy of product. So this, again, was a spontaneous reaction, or endothermic, you can think of it. This little cross symbol up here is the transition state. So that is a form of it's halfway between reactants and products. But that energy is lowered when you use a catalyst. We're not going to get into specifically how that happens, but just appreciate that it does happen when a catalyst is present. In our bodies, catalysts are not metal-containing compounds. They are called enzymes. And they stabilize this transition state, so the reactions are greatly sped up. I'm guessing sometimes hundreds of thousands of times they're sped up in biochemical reactions, maybe millions of times. So here's what we call a lock and key picture of how an enzyme works. So we call it an enzyme substrate complex that forms in a biochemical reaction. Enzymes are usually proteins, and what happens is, this is a schematic diagram. These molecules here are just some sort of smaller molecule, maybe a protein that you've eaten that needs to be broken down. And what an enzyme will do is, to digest the food, it will bind this protein and provide a place for a reaction to occur. And what happens after the reaction occurs is the products come out of the enzyme's active site, and the enzyme is then unchanged. It just goes on and can then accommodate another substrate. But only substrates that have a very specific shape will fit. Molecules that have different shapes, like these, would not fit inside this particular enzyme's active site. So enzymes are very specific. Each enzyme will catalyze only one specific reaction. And if you read anything about this, you'll notice that the names of enzymes almost always end in the suffix ase. There are proteases, catalases. There's an enzyme called DNA polymerase, which is an enzyme that helps DNA molecules get constructed in cells. There were some early catalysts that were discovered that are named, I think there's one called trypsin, chymotrypsin, and pepsin. They don't end in ase, but they realized that many years ago that there were so many enzymes that they had to come up with a standard way of naming them. So they came up with this suffix ase, so they all end with that suffix, you'll notice, if you read anything about enzyme chemistry. I also want to show you a more specific diagram. Since this is a chemistry class, I want you to have some understanding of what's going on in these active sites with atoms, not just some schematic diagram. So, as you know, our body temperature is about 98.6 Fahrenheit, which I believe is around 37 degrees Celsius. Cells have to stay at that temperature. The temperature can't go much below that or much higher than that, otherwise we run into big problems. Cells will die and reactions will stop. So, as you know, enzymes are our body's catalysts, and they have this active site. This lock and key model was proposed around 1890. So this diagram here is just showing what I just had on the previous handout a little more specifically. So I'm not going to expect you to draw all of this, but just have a general understanding of what's going on here. So what's going on here is this blue molecule. If you can see, that's blue. I'm not sure if it's showing up on the camera, but this is a dipeptide. A dipeptide is like a protein. It's just a very small protein. It's only made out of 2 amino acids. The proteins that you would eat in food are, I'm guessing, hundreds and thousands of atoms long. But just to simplify the picture, I've drawn a dipeptide. A dipeptide just means it's made of 2 amino acids. Amino acids have these characteristic structures. They have an end that has a nitrogen atom, that's the amino end, and they have an end that contains this carbon and 2 oxygens here. That's called a organic acid. So that's where the word or the phrase amino acid comes from. So what happens is when you, in biochemical reactions, if this dipeptide needs to be broken down, it needs an enzyme in a cell. So the enzyme, particular enzyme for this, would be called a peptidase. There's the ASE ending I'm talking about. Or it might be called a protease. But what it does is its active site is a very specific place somewhere along the long chain of the protein molecule that will only accommodate this specific molecule. And how it does that is it has specific functional groups. It might have an acid group here in red, an amine group here, and another amine group here. Notice some of the amines are electrically charged and some of the acid groups are electrically charged. That depends on the pH of the cell. If the pH of the cell is just right, you can have the hydrogen atoms be transferred between the acid and the amine, which is a basic functional group. Acids and bases react together. So the red atoms represent atoms that are inside the enzyme. They don't move. They just provide a docking station, so to speak, for the dipeptide. The dipeptide is held in place for a fraction of a second. These biochemical reactions happen on a millisecond, microsecond, millionths of a second timescale, very, very fast. So it comes in here. It's held in place because of what are called intermolecular attractions. The intermolecular attractions, in this case, this is a dipole force. It's just an ionic attraction between positive and negative charges, as is this one. This force here is a very important intermolecular force in biochemistry. It's known as a hydrogen bond. A hydrogen of one molecule is attracted to an oxygen of another molecule. This is the same intermolecular force that holds DNA strands together. It's extremely important, and we will discuss it further later on in the course when we talk about the behavior of gases. But let's say a water molecule needs to come in. So the water needs to find the dipeptide, and if the dipeptide is held in place for just the right amount of time, a water molecule will easily find it because it's not moving, and the water molecule will attack this carbon. And what happens is this bond right here breaks, and you form two amino acids. You pretty much break this molecule in half. That's how our bodies carry out chemical reactions. This reaction, if it weren't held in this active site, would take who knows how long. It would take too long for it to be of any use to us. So we've evolved to have these enzymes that will greatly speed up these chemical reactions. So that will finish our discussion of kinetics. I hope you found this video useful. Please go back and watch it again and take good notes, and we will continue on our discussion in the next videos. We're going to move into what's called equilibrium in the next chapter. So good luck, and we will see you in the next video.